In this lesson, we're going to get started talking about the absolute value function graphs by hand. And in order to graph it by hand, we want to have some understanding as to what the absolute value functions will be shaped like. And you have seen some of the absolute value function graphs through the applications already. And in general, we say the absolute value function because it will never take the negative value. It'll always stay above the x-axis. And generally, the shape of the absolute value function will be a v-shape overall. And if we only have the absolute value expression for the entire function, we would have that turning point hitting exactly on the x-axis over here. And on the x-axis, we know that our y value is going to be equal to 0. So the function value is equal to 0 over here. And that should be our turning point. And that's a very important point for us to graph absolute value functions by hand. This will help us think about what points we can pick in order to have a more complete graph, and in particular we definitely want to include that turning point as one of the key features to include in our graphs over here. And with that in mind, we can take a look at the first example. In the first example, our f of x is equal to the absolute value of 1/2 x minus 1. So to find the turning point, remember we said that's where the function value is equal to 0. The only time the absolute value is equal to 0 is when whatever is inside is equal to 0. So that's really the first part we want to consider, is the turning point. The turning point of this function happens when 1/2 x minus 1 is equal to 0. And this becomes a linear equation that we're pretty familiar with solving by now. So to solve it, we can add 1 on both sides and get 1/2 x is equal to 1, and therefore multiply by 2 on both sides gives us x is equal to 2. So that's a turning point. And with that being the turning point, it tells me when I want to make a table to pick the ordered pair to find and graph, I want to pick the points that's centered around x equals 2. And that's how I find the guidance on how I would start the table. And again, we can aim for finding 5 points just so that we get a more detailed graph at least. And I would put 2 kind of in the center. That's a middle value, or the point that I know is a turning point I'm going to pick. As x equals 2, I already know the function value is equal to 0 based on our description. And for the other points you want to pick, you can have a little bit more freedom in terms of what values you want to pick. And because I know x is getting multiplied by 1/2, so I'm going to aim for picking some even numbers just so I can get easier calculations throughout the process. If I pick the even values, I can go for the next number being, let's say, 6, for example. And if the next number is 6, we have 6 times 1/2 will be 3, 3 minus 1 will be 2, and the next value being 10. You can pick any even number at this point, and we would get half of 10 would be 5, 5 minus 1 is 4. And then for the part that's smaller than 2, we can pick, for example, 0 will be a pretty easy choice. And that also shows us the y-intercept as well. If we pick 0, we would have the absolute value of -1, which turns out to be +1. And then if we pick the next value, we can do -2, for example. And half of that will be -1, minus 1 is -2. So absolute value of -2 will be +2. So these are the 5 points I picked. Feel free to pick some different points and see whether your graph still matches what I have over here. And with the values I have, I can go ahead and start scaling things. And since none of the values are super big, I'm just going to go ahead and go up by 1 every time. So every 2 boxes will be 2, 6, and 10. Similarly, this will be 0, this will be -2. And we would have -2, 2 over here. You don't even have to label the negative side of the y-axis because we know you won't have negative values over here. And then we get 0, 1, 2, 0, 6, 2, and lastly 10, 4 over here. So even though the points to the left of the turning point seems like they're closer together, once you connect it, you should notice that they are indeed all the same slope, or the symmetric image of the other side. So that would be my graph over here once we connect everything, and we would want to draw the arrows to tell us we can keep going on either side. X can take any real number of values, and this is how we create a graph for the function, absolute value function, by hint. And if you check your graph, basically if you use the turning point as the axis of symmetry, or where the turning point is as the axis of symmetry, you will see the two halves are exactly mirror image of each other. They should have exactly the negative slopes of each other. If this part has a slope of 1/2, this part would have the slope of negative 1/2. And that's how we can go about graphing this. And next, let's take a look at another example and see how that plays out with the strategies we talked about. And here, if we want to work with g of x in part B, first we can still work with the turning point idea first. And to find the turning point, we just set whatever is inside the absolute value to be 0. To solve that, we can add 3x on both sides. To get 6 is equal to 3x, divide both sides by 3, we will get 2 is equal to x. Again, the turning point is 2 in this case. And I will still put 2 over here, and that one we already solved. G of x is equal to 0 at that point. Then for the next points, we can still do similar things. I'm just going to go up by 1 every time for picking the numbers, just because I know the slope for inside the absolute value is -3, so the numbers will change values for the function value will change pretty quickly if I change x value to be really big. And then I can pick x equals 3, 4, and on the other side I can pick 1 and 0. I'm just going to pick the symmetric points this time. So starting from 0, again, I like to incorporate x equals 0 in the graph to also find where the y-intercept is going to be. And then if I have 0 plugged in, I would have absolute value of 0 plus 6, which would be 6. And if we plug in 1, we would have -3 plus 6, which should be +3. Next, if we plug 3 in, we would have -9 plus 6 will be -3, but absolute value of -3 would be +3 again. Similarly, if we plug 4 in, we get -12 plus 6, which is -6. Turning into the absolute value of -6, we get +6. So these are the values we have, and you can see because we picked symmetric points around the turning point, we should have symmetric values in the table for g of x as well. With that said, we can go ahead and scale things. So we get, again, each box can be 1. Similarly for the y-axis. Alright, so here I had the first point being 0, 6, and then the next point 1, 3, 2, 0, 3, 3, and 4, 6. So these are the points. You can see this graph is pretty narrow over here, and that's directly because the slope is much steeper over here. The slope is a larger value, or larger absolute value, than the 1/2 we had in the previous example. So connecting the points, we will get this graph over here. And in this case, again, we want to put the arrows over here, and that would be the graph for our function g of x. And as we talked about, if you have the slope absolute value to be smaller, closer to 0, you would have a wider, flatter graph. As you have the slope value, the absolute value of the slope being larger, basically in this case the absolute value of the slope being 3, you would have a narrower graph that's going to be taller overall. And this is going to be these are the key points for graphing the absolute value functions. And remember, it's always going to be the V shape that we're looking for, and your graph should always stay above the x-axis, and the turning point will hit at the x-axis exactly at the key point we want to graph over here.